Okay, so this is Newton's famous formula for the universal gravitation. And it's actually one of my favorite equations of all time. So here's how you interpret the force of gravity equals the mass of object 1 times the mass of object 2 divided by the square of the distance between the two objects' centers of mass times the gravitational constant, the universal gravitational constant that had to be determined experimentally. Now I want to talk a little bit about this, but first I wanted to say that remember, when you're solving these problems, force is always measured in newtons. In this case, mass is going to be measured in kilograms, and distance is going to be measured in meters, not kilometers or miles, but in meters. And we won't really worry about the units for the gravitational constant because they're kind of funky and weird. But I'd like to talk a little bit about g for a second. So we haven't worked much this year with constants. Basically, think of it this way. G is a correction factor because the universe doesn't know that we measure force in newtons, we measure mass in kilograms, we measure distance in meters. So we had to experimentally determine, basically, this. What is the amount of gravitational force that would be exerted if we took 1 kilogram of matter, placed it 1 meter away from another kilogram of matter, and measured the gravitational force of attraction between the two? Well, if we were able to do this, what we would find is the force of attraction between these two 1 kilogram masses placed 1 meter away would be 6.67 times 10 to the negative 11 newtons. So we can use this value here, 6.67 times 10 to the negative 11. That is the universal gravitational constant. It is a correction factor that we have to figure into the equation in order to be able to calculate gravitational forces given certain masses in kilograms and distances in meters. So let's just try an example of one of these problems. How much would a 65 kilogram astronaut weigh on a planet that has a radius of 5.7 times 10 to the 6 meters and a mass of 3.6 times 10 to the 25th kilograms? Always, I advocate that you first look through this and try to figure out what exactly is it we're trying to find. In this case, what we're trying to find is the weight of the astronaut. And weight is the force of gravity acting on something. So we're solving the gravitational equation for force. We have mass 1 here, mass 2 here. We have a distance here, which we have to remember to square, and then we multiply by the gravitational constant. So what we're going to do is we're going to substitute into this equation here. We're going to use F equals G m1 m2 over d squared. Don't forget the squared part. Everybody always does. So let's substitute in. G is always the same. The gravitational constant is always 6.67 times 10 to the negative 11th. M1 is the mass of our astronaut. M2 is the mass of the planet that she is standing on. And then D is going to be the radius of the planet. How far is it between her center of mass and the center mass of the planet? We were told that is 5.7 times 10 to the 6th meters. Don't forget to square that. Now, when we do this, we want to remember to use the EE key on our calculator. So if you'll recall, kids, what we're going to do is this. We've got to make sure that when we do this, we say 6.67 second function of the comma, which is right above the 7, puts us in the EE mode, and then we can just type the negative 11. Okay, so 6.67 times 10 to the negative 11 times 65 times 3.6 EE button 25, enter. That gives us this value right here, 1.56 times 10 to the 17th. We won't worry about the units right now. Then we have to divide that by 5.7 times 10 to the 6th squared, which turns out to be 3.24 times 10 to the 13th. Again, don't forget your EE button and don't forget to square it. And when we divide this by this, what we'll find is, standing on that planet, she weighs 4,814 newtons, which is a lot, which would basically be the equivalent of weighing about a little over 1,000 pounds on Earth.